Hi, good morning, everyone. Good morning. People online, good morning. Can you hear me?
Yes, sir.
Right. We just started with oscillators, no? Right. So, guys, what is an oscillation? A particle or an object moving through and back towards a fixed point is what we call an oscillation. Correct? So, a simple example is when an object is attached to a spring and when you move the object from the equilibrium point to a side and leave it will oscillate. Okay. So, and then an oscillation becomes a simple harmonic motion when two conditions are satisfied. Yes. What are the two conditions? The acceleration of the object which is in the oscillation has to be in such a way the acceleration is directly proportional to the displacement. So you increase the displacement, the acceleration will increase. And when the acceleration is when the displacement is decreasing, the acceleration will decrease. If the oscillation is in such a way, the acceleration is directly proportional to the displacement, and also the second condition, the acceleration and displacements are in opposite direction, then that oscillation becomes a simple harmonic motion. You remember? Yes, acceleration and displacement are in two opposite directions. So that means when the displacement is, let's say this is a fixed point, the displacement is increasing this way, the acceleration is towards that fixed point. And when the displacement is in the other direction, the acceleration will be in the opposite direction, towards the fixed point. So acceleration and displacement are in opposite direction, and acceleration is directly proportional to the displacement, then it becomes a simple harmonic motion. These two conditions need to be satisfied. So A is directly proportional to x, and then the equation becomes A equals minus omega square x, which is the minus sign says that A and x are in opposite direction. The omega square is a proportionality constant, which is the omega is known as this what? Angular frequency. Correct? So omega is equal to 2 pi over t, where t is the time period of the oscillation, or 2 pi f, where f is the frequency of the oscillation. Am I right? Correct? And then we have copied up to this point, I guess. Okay. So using, guys, give me a minute. Hold on. Okay, right. Then using f equals ma, f equals ma, and a is minus omega square x. Since m omega square is a constant, f is equal to minus here. That part is not. Did I ask you to copy that? No, no. Okay, forget about it.
We told us not to copy it, sir.
Yeah. Forget about that. Write down a question. An object of mass 0.5 kilogram an object of mass 0.5 kilogram is attached to a spring and it is in simple harmonic motion. It is in simple harmonic motion with a time period of 0.8 seconds. With a time period of 0.8 seconds. Full stop. Calculate its acceleration. Calculate its acceleration. And the resultant force acting on it. And the resultant force acting on it. When its displacement is 5 centimeters. When its displacement is 5 centimeters. Okay. Right, guys, acceleration is given by A equals minus omega square x. But if you forget about the minus sign is just for the direction. We can take it as A equals omega square x to find the magnitude of the acceleration. So omega is equal to 2 pi over t, which is 2 pi over the time period is given 0.8. Okay, that is the omega. So A equals omega square x. Omega is 2 pi over 0.8. And that needs to be squared into the displacement is 5 centimeters, which is 0.05 meters. That will give you the acceleration when the displacement is 5 centimeters. That is 3.08 meters per square seconds. That is the acceleration. And when it is having this acceleration, we are told to find the acceleration and the resultant force acting on it. To find the resultant force, F equals ma. The mass of the object is 0.5 into 3.08. That will be 1.54 newtons. That's the resultant force acting on the object. Okay. Right. The next one. An object of mass 0.2 kilograms. An object of mass 0.2 kilograms is attached to a spring. Is attached to a spring. An object of mass 0.2 kilogram is attached to a spring, and it is in simple harmonic motion. It is in simple harmonic motion with a frequency of 20 hertz. The frequency of 20 hertz. Calculate its acceleration. Calculate its acceleration. And the resultant force acting on it when its displacement is 8 centimeters. That's the answer. What is acceleration? Okay, acceleration is 1263. And the resultant force is
Sir, I got
200.
it, sir. I thought that is wrong. It's the big value.
Sorry,
I got that, but I thought it's big, too much of a big value.
what did you get?
1263.
No, that's correct.
Yeah.
So time period is the reciprocal of frequency. 1/20, that is 0.05 seconds. So the omega is 2 pi over t, which is 40 pi. Then use A equals omega square x. And the acceleration, we need it at a displacement of 8 centimeters, which is 0.08 meters. To get the answer, then use F equals ma. Same thing as the earlier one. Okay.
Yep.
Right. The next one. Right on the next subtopic. Displacement and velocity.
So what's the one before that?
Okay. Right. Displacement and velocity. Displacement and velocity. Because now let's say there is an object attached to a spring, and this is the equilibrium position. And then you pull it down to this position. So this then distance becomes the amplitude. And at t equals 0, when the time is 0, you release it. Okay. So it's when the time is t, let's say it has a displacement x from the equilibrium point. Then if it is a simple harmonic motion, it will have an equation like this. The displacement will be x equals a cos omega t, where x is the displacement, a is the amplitude, and cos omega t, omega is the angular frequency, and t is the time. So using this equation, you can find the displacement of the object, which is in simple harmonic motion when the time is t. Okay. And velocity will be given by minus a omega sine omega t. Okay. Who are the students doing maths here? Okay. What is the differentiation of cos 6? Minus sine. Yes. So if you differentiate displacement with respect to time, you're supposed to get the velocity. So dx by dt is equal to a is a constant. A cos omega t differentiation will be minus sine omega t into the differentiation of omega t is omega. So that brings you minus a omega sine omega t. That is how this equation is derived. Okay. So those who don't do math, you don't have to worry about it. You just need to know the two equations. X is a cos omega t. Velocity is minus a omega sine omega t. Okay. So if you differentiate x with respect to time, you will get the velocity. Take it up. Okay. Right.
So can I go back for 1 second, sir, please? Thank you, sir.
Answer the Vijesh. Baru is first row. Navik. Right. Linuki. Sound. Banchana. Good. Bhavin Bala. Mariam Sadini. Oh, not bad. Mariam Sadini. Ishaq Miski. Zakir Azmi. Atika. Sumeha Shahid. Kirtigan. R. Kirtigan. Tahir Jagri. Amman. Okay, right. Guys, now A equals minus omega square x, right? So if A is minus omega square x, the acceleration. So into this equation, if I replace the x with A cos omega t, instead of x, if I substitute A cos omega t, you will get this equation. Acceleration equals minus omega square A cos omega t, which is acceleration in terms of time. Okay. Take that down. And also, we know omega is equal to 2 pi over t. So if you replace the t with 1 over f, you will also get omega equals 2 pi f. Take that down as well. Right. Guys, now you know acceleration is directly proportional to the displacement. So when an object is moving in simple harmonic motion, acceleration will be maximum where? There will be the acceleration maximum. No, I'm asking in terms of displacement. A is directly proportional to x, right? So if when A will be maximum, when the x is maximum, right? So the x is maximum means when it is at the amplitude. So the acceleration of an object will be maximum when it is at the amplitude. Okay. And also the acceleration will be minimum. The minimum value of the acceleration will be 0. So that will be 0 when the x is 0. Correct? is equal to minus omega square x. So A will be 0 when the x is 0. So x is 0 means when it is at the equilibrium point. Correct? So if a particle is oscillating, when it is at the extreme ends, at the lowest point or the highest point, when it is at the amplitude, acceleration is maximum. And when it is passing through the equilibrium point, the acceleration is 0. When x is 0, the acceleration is 0. Take it down. Under that in point forms, the acceleration of the object will be maximum the acceleration of the object will be maximum at the amplitude, and it will be 0 at the equilibrium point. Okay, and now the next point, the velocity of the object will be 0 at the amplitude. The velocity of the object will be 0 at the amplitude. And it will be maximum at the equilibrium point. And it will be maximum at the equilibrium point. Okay,
So, equilibrium point is x equal to 0.
where x is equal to 0, displacement is 0. Right, so guys, I'll take the same example again. Let's say there is this object which is attached to the spring, is oscillating. Let's say this is where the x is 0, the equilibrium point. This is where the object is at the amplitude. Okay. So at this point, at the equilibrium point, the acceleration is 0. V is maximum. Velocity is maximum. Correct? At the amplitude, velocity is 0. Acceleration is maximum. That's what we have written. Okay. So it's super obvious why the acceleration is maximum at the equilibrium point, because A equals omega square x. So A will be maximum when the x is maximum, that is at the amplitude. And A will be 0 when x is 0. So at the equilibrium point, the acceleration is 0. But if you take the velocity, velocity is given by minus a omega sine omega t. Right? Velocity is given by minus a omega sine omega t. Okay. It is maximum when it is at the equilibrium point here. And when it is at the amplitude, when it goes to the amplitude and it changes direction. When you throw an object, you know, when you throw an object at the maximum height, what is the velocity? 0. Just before it changes the direction, the velocity is 0. So if you take this object which is in simple harmonic motion, when it goes to the amplitude, it is momentarily 0, and the next moment it's going to change its direction. Okay, just before changing the direction, when it reaches the extreme end, the velocity becomes 0. Remember these 2 points. Okay, fine. write down a question. A pendulum sorry,
Go back to the page where the velocity and acceleration. Slide.
okay, write down a question. The pendulum that operates a grandfather clock is released from its amplitude position which is 10 centimeters from the middle, which is 10 centimeters from the middle. Full stop. It swings completely. It swings completely through one cycle. Every 2 seconds. Every 2 seconds, full stop. What is its angular velocity? What is its angular velocity? And what is its displacement? And what is its displacement after 174.5 seconds and hold on. Hundred and 87.3 seconds. So the question has 3 parts. One is to calculate the angular velocity, and then to find the displacement at 174.5 seconds, and the next one is to find the displacement at 187.3 seconds. Okay. Right. So guys, the angular velocity omega will be 2 pi over t. So time period is 2 seconds. It swings completely through one cycle every 2 seconds. So that means the time period is 2. So it will be 2 pi over 2. So that is pi radians per second. That is the angular velocity. Okay. And then to find the displacement, we have this equation. X equals a cos omega t, right? That is the equation, right? So amplitude is 10 centimeters. Cos omega is pi. Into the t is the first part is 174.5 seconds. But make sure the candle is in the radian mode. Put the candle in the radian mode. And check 10 cos pi into 174.5. You will be getting the
It's not.
answer 0.
It's 10 cm, so it's
No, doesn't matter. I will be getting the answer in centimeters.
don't give it a unit standard.
No, for this question. That is the displacement when the time is 174.5. When the t time is 187.3, x equals 10 cos pi into 187.3. How much is that? Minus 5.88. That's in centimeters. That is the displacement when the time is 187.3 seconds. If you take it in meters, you will get the answer in meters. If you take it in centimeters, you will get the answer in centimeters. No problem. Okay.
That means it moves backwards along the x-axis by minus.
It's in the passing the origin, it has gone to the other side.
Yeah, so it moves backwards along the x-axis, right? To the
What do you mean by the left here?
left of 0, left of x equal to.
Yeah, it's on this side. You don't know which way it is moving, but it is on to the negative side. Based on that, you can't tell which way it is moving, but you know where it is. It is on the other side of the equilibrium point, not on the side where it started. Okay.
Then how do we know that started, whether it started at x equals 0, x equals
Question says it released from its amplitude. So it started from the extreme end. It started from the extreme end,
extreme?
the amplitude. You pull it from to one side and you release it. Okay. From the amplitude, you have released it. So now it is in simple harmonic motion. So at 187.3 seconds, the displacement is not on the side that you released it. It is on the other side.
That side of the absent delta last answer.
Right. Guys, write on the next one. A science museum. A science museum has a giant demonstration tuning fork. Full stop. The end of each prong vibrates in simple harmonic motion. With a time period of 1.2 seconds. With a time period of 1.2 seconds. And starts vibrating from an amplitude of 80 centimeters. from an amplitude of 80 centimeters. From an amplitude of 80 centimeters, full stop. Calculate the displacement, velocity, and acceleration after 5 seconds. Okay, done. Right. So guys, to find we know the time period is 1.2. So omega will be 2 pi over t.
So for the acceleration, in this acceleration, should you use the minus or no minus?
No need. Just the magnitude is needed. So 2 pi over 1.2. That is 5 pi over 3 radians per second. That is your omega. So to find the displacement at 5 seconds, we can use omega x equals a cos omega t. The amplitude is 80 centimeters. I'll take it in meters this time. 0.8 meters. Cos omega is 5 pi over 3. T is 5 seconds. That will give you the displacement 0.8 into cos. That's I'm getting 0.4 meters. or if you have got it in centimeters, it would have been 40 centimeters. Correct? Yes? You know how to get it in radian? Can you help her? You have to change the mode in the calculator. You know how to change the mode, right? From the calculator, you all don't know how to change the calculator radian. Are you serious? If you have this calculator, press the shift and press the mode button. Shift and the mode button. Under that number 3, you will see degrees, DEG. Number 4, you will see RAD, radian. So if you press 4, it will fall to radian mode. If you press 3, it will fall to degree mode. Did you find it? Once you put it to the radian mode on the calculator, here you will see the letter R. If you put it to degree, you will see the letter D. Anyone still couldn't find it? No? Found it? Anyone? Okay, no? Right. Then calculate the displacement done. Calculate the velocity. To find the velocity, we use the formula minus say omega sine omega t. Am I right? So substitute A is 0.8. Omega is 5 pi over 3 into sine omega is 5 pi over 3. T is 5. That will be again 3.63 like. Okay. Meters per second. Or if you have got it in centimeters per second, it will be 36.3 centimeters per second. And then finally, to find the acceleration, I can use A equals omega square x. Omega is 5 pi over 3. That square into the x is 0.4. So 5 pi over 3 squared into 0.4. 10.96, 10.97. I'll take it as 11.0 meters per square second. Okay. You'll still get the same answer. We differentiate velocity with respect to t, you will be getting once again minus a omega square cos omega t. And substitute into that the value of p, you will get the same answer. Thank you. Right. Do another one. An object in simple harmonic motion has a frequency of 50 hertz. An object in simple harmonic motion has a frequency of 50 hertz and an amplitude of 12 centimeters. and an amplitude of 12 centimeters, full stop. Calculate its displacement, velocity, and acceleration at t equals 12 milliseconds. Time is 12 milliseconds. Done. Are you getting the displacement as minus 0.097 meters? Have you? To find the omega, you can use omega equals 2 pi f or 2 pi over t. Actually, don't think about this sign. Forget about the sign. Just get the magnitude, that's enough. Here the sign is only to state the direction. So I want to get the value. Forget about these minus signs, really just look at the value. And velocity is 22.2 meters per second. And the acceleration is 9,574 meters per square second. Have you got these values? Yes. Right, guys, write down the next subtopic. Graphs in simple harmonic motion.
So I got 9,581.
Okay, so close enough.
And I got acceleration at time t, sir.
At time t, what is the equation you use?
Omega squared into a cos omega t.
Okay, fine, no problem. Here I have taken the approximated value of x, which is 0.097. That is the difference. Right, graphs in simple harmonic motion. Part A, displacement versus time. So, guys, we know x equals a cos omega t. So if you sketch a graph of displacement versus time, it will be a graph in the shape of a cosine graph. Okay. It will take exactly a time period t to make one complete oscillation. So when the time is t, it has made complete oscillation. Here it's t over 4, here it's t over 2, here 3t over 4, and so on. Can you draw this graph? Okay, right, that was part A, displacement versus time. Part B, velocity versus time. Velocity versus time will be a very similar graph, but it's minus a omega sine omega t, again a sinusoidal graph. When the t is 0, the velocity will be 0 because it is at the amplitude. And it will have a variation like this. This is the displacement graph. This is the velocity graph, velocity time graph. Okay, right, acceleration versus displacement, part C. Acceleration versus displacement. That will be a straight line graph because acceleration is directly proportional to the x with a constant gradient. But it will be a negative gradient because we know acceleration and displacement are in opposite direction. So when the displacement is positive, acceleration will be negative. When the displacement is negative, the acceleration will be positive. Okay, because of the minus sign. It's a equals minus omega square x. A equals minus omega square x. So gradient will be a negative gradient. Okay. Right on the next subtopic. The variation of velocity with displacement. Variation of velocity with displacement. So the previous equations that we met for displacement and velocity, that was in terms of time. Now the relationship between velocity and displacement, according to the displacement, how the velocity changes is given by this equation, which is v square equals omega square times a square minus x square, where v is the velocity, omega is angular velocity, angular frequency, a is amplitude, and x is the displacement. So at a particular displacement, the velocity is given by this equation. Take it down. Those who did the exam physically, please come and collect your papers. Those who did it online, your papers have been mailed back to you. Okay. Right. Guys, the velocity is maximum where? At the equilibrium point. That is when x is equal to 0. So we can find an expression for the maximum velocity of the particle in simple harmonic motion by substituting x equals 0. So V max square is equal to omega square into a square minus 0. X is 0. So then V max square is equal to omega square into a square. That is V max square. So V max is equal to square root of that, which is omega 8. So the omega multiplied by the amplitude will give you the maximum velocity of a particle which is in simple harmonic motion. Take it down. Okay. Any questions? Read in a question. An object in simple harmonic motion. An object in simple harmonic motion has an amplitude of 5 centimeters and a frequency of 0.25 hertz. Amplitude of 5 centimeters and a frequency of 0.25 hertz. Full stop. Calculate its velocity when the displacement is 2 centimeters. That's part A. And part B is its maximum velocity. So you can find the omega using omega equals 2 pi f and use the equation v square equals a square into, omega square into a square minus x square. Right, so guys, omega is using 2 pi if 2 pi into 0.25, omega is 0.5 pi. Then using the equation v square equals omega square a square minus x square, I'm getting the v is 0.072 meters per second. That's part A. Then the part B is its maximum velocity, which is using omega A. Omega is 0.5 pi into the A is 5 centimeters, that's 0.05 meters. That is 0.079 meters per second. Have you got these answers? Okay. Right? Do another one. The next question. An object in simple harmonic motion has an amplitude of 20 centimeters and a time period of 2 seconds. An object in simple harmonic motion has an amplitude of 2 centimeters and a time period of 2 seconds. Full stop. Calculate its displacement. Calculate its displacement when the velocity is 0.4 meters per second. right? So omega is, I found it to be 2 pi over t, time period is close to omega equals pi radians per second. So guys, use the equation v square equals omega square into a square minus x square. That is 0.4 square equals pi square into 0.2 square minus x square. When you solve that and get the x square subjected, you get something around 0.20238, blah, blah, blah. So when you take the square root, you will get the x. So when you take the square root, you can take both plus or minus. There are two displacement values. The reason from the equilibrium point, there are two sides at 2 points at which both it will be having the same velocity. Okay, 0.4 meters per second. There are 2 points. It can have the same velocity. One is on one side of the equilibrium point. The other is the exact same amount of displacement in the other side of the equilibrium point. Is that okay? So that's why it is plus or minus 0.154 meters. Correct? Right. Then the next subtopic, time period of a simple harmonic oscillator. Right. So guys, let's consider a spring which is having a spring constant K and a mass M is attached to it. Okay, look at this. There is a spring with a spring constant K and a mass M attached to it. Then you pull it down and release it. It will oscillate. Okay. The time period of that oscillation is given by 2 pi square root of M over K if it is a simple harmonic motion. Okay. Does that depend on the amplitude? No. Whether you move the object 1 centimeter down, 2 centimeters down, or 3 centimeters down, it doesn't matter. As long as it is a simple harmonic motion, its time period will be the same. It is given by 2 pi square root of M over K. It doesn't depend on the amplitude. It depends on the mass of the object and the spring constant of the object. Exactly. It doesn't depend on the amplitude. Take it down. Okay, done? Right. And the next subtopic, time period of a simple pendulum. Time period of a simple pendulum. Right. Because if there is a pendulum with a length L, Okay. If you move it to a side, if you give it a displacement and release it, it will move in a simple harmonic motion. And if it is moving in a simple harmonic motion, the time period is once again given by 2 pi square root of L over G. Okay. So again, it doesn't depend on the amplitude. Whether you move it 1 centimeter to the right or 2 centimeters to the right, it doesn't matter. As long as it is a simple harmonic motion, it will depend, the time period will only depend on the length and the gravitational acceleration. If you increase the length, time period will increase. Okay. Take it down. Okay. Not in the syllabus definition.
Because these two don't make sense.
Why is that?
They just don't, because I don't know any of that.
Yeah, exactly. So there's nothing in the syllabus. So there should be something, but definitely not. We don't know. Right, make a note under that. The time period of the simple harmonic motion. Time period of the simple harmonic motion. Time period of the simple harmonic motion doesn't depend on.
So simple pendulum, right?
No, simple harmonic. I'm giving a note for common both for the spring and the pendulum. So that's what I meant here. Time period of the simple harmonic motion doesn't depend on the amplitude of it. Okay, right. Write down a question. A mass of 2 kilograms and a spring with a stiffness 2 into 10 to the power 5 newtons per meter is used to make a simple harmonic oscillator. Stop. Calculate its time period. Just a matter of using the equation. A equals 2 pi square root of m over t. Sorry? Come again? Yeah, G is gravitational. Are you getting 0.02 seconds? Okay, guys, you can take a break. See you in 15 minutes. Right, question 2. A simple harmonic oscillator has a frequency of 20 hertz. Full stop. What is the stiffness of the spring? If the mass used is 4 kilograms. The mass used is 4 kilograms. Same equation. Done. What is the answer? 6.3. 63,165 newtons per meter. See? So use T equals 2 pi square root of m over k. Frequency is 20, means the time period will be 1 over 20. 2 pi square root of m is 4. So square root of 4 over k. From that you need to get the k subjected. 63,165 newtons per meter. Okay. The next one. Question 3. A simple pendulum.
Sir, can you go back for 1 second, sir, please?
Right.
Oh, sir.
A simple pendulum has a length of 2.7 meters. 4.7 meters. Calculate the frequency of its oscillation. Calculate the frequency of its oscillation. That's the answer. So you use t equals 2 pi square root of L over G and find the time period, and the frequency is what needed. Frequency will be the reciprocal of the time period. I get in 0.303 hertz. Okay. And the next one. Question 4. A simple pendulum has a time period of 4.5 seconds on Earth. A simple pendulum has a time period of 4.5 seconds on Earth, where the gravitational field strength is 9.8 newtons per kilogram. Full stop. Calculate the time period of this pendulum on Moon, where the gravitational field strength is 1.6 newtons per kilogram. Don't know, we'll see. Don't know, we'll see. Not sure. The answer. 11.13 seconds, correct. So you can take t equals 2 pi root L over G. So if you square both the sides, t square equals 4 pi square into L over g. So t square into g equals 4 pi square L. 4 is a constant, pi is a constant, L is a constant, same pendular. So which means basically t square into g is constant. Correct? So t square into g on Earth is the same as a t square into g on Moon. Okay? So on Earth, the time period is 4.5. So 4.5 square into g is 9.8. That is equal to the t square g on Moon, which is t square into the g is 1.6. From there, you get the t subjected, which is 11.13. This is one way of doing it. They have done some other way and got 11.13. That's fine.
You can get the ratio of the field strengths and then root that and then multiply that by.
Correct. Still get the same answer. Because t is inversely proportional to the square root of g. Okay. Right. Then right on the next subtopic. Conservation of energy. Let's hold on. Wait for a minute. And then the subtopic conservation of energy during simple harmonic motion. Conservation of energy during simple harmonic motion. Okay. So guys, now if I sketch a graph of, okay, kinetic energy. When an object is in simple harmonic motion, if I sketch a graph of kinetic energy, now let's say this is displacement. This is EK. kinetic energy. Where is the speed maximum? At x equals 0. And when at the amplitude, the kinetic energy is 0. Speed is 0, so the kinetic energy has to be 0. So if I sketch a graph of kinetic energy versus displacement, at the equilibrium point, kinetic energy will be maximum. Okay. At the amplitude, speed is 0, so the kinetic energy is 0. So it will be a graph like this, where it will have a parabolic shape. Okay. So here the displacement is amplitude, which is A. Here it is the minus of that, which is minus A. So
Just y equals x square.
a minus of that.
Y.
Take it now. So kinetic energy will be maximum at the equilibrium point and 0 at the amplitude. Right? Done. And if you take the potential energy, it will be a graph like this. It will be zero at the equilibrium point and maximum at the amplitude. So it will be a graph like this.
Which potential?
Elastic. Okay. And then part C. If you take the total energy, which is a sum of kinetic and potential energy, how will be the graph?
Always
It will be a constant. The total energy will not change. It will remain the same.
so that we also change it.
Small change.
But we don't know, like some pendulums, like it can give like some wide range of.
Correct. Then that should also be taken into account. This is minus A naught. Sorry, not minus A. This is plus A. With the displacement, total energy will remain constant. Okay.
So there are no energy losses.
I mean, if you look at an ideal situation, no, but practically, yes. Right. Guys, question number 1, page number 1. A 150 gram mass is hung from a vertical spring. The mass is displaced from its equilibrium position and oscillates vertically with simple harmonic motion. The graph shows how the elastic potential energy varies with displacement of the mass from the equilibrium position. Add a line to the graph to show how the total energy of the mass spring system varies with displacement. So guys, the total energy if you take, that will remain a constant. So it's going to be a graph like this. Total energy will remain constant. Agree? Determine the speed of the mass. Determine the speed of the mass when its displacement from the equilibrium position is 1 centimeter. Determine the speed of the mass when its displacement from the equilibrium position is 1 centimeter. Guys, now look at this one. Yeah, they're asking for the speed. So now when the displacement is 1 centimeter, I can find here what is the elastic potential energy at 1 centimeter. Can you tell me what is the elastic potential energy? 4.5 millijoules, right? 4.5 millijoules. So if that is the elastic potential energy, tell me what is the total energy? What is the total energy? 19 millijoules. At any instance, the total energy is 19 millijoules. So what will be the kinetic energy then? 19 minus 4.5. How much is that? 14.5 millijoules. That is the kinetic energy. Okay. Kinetic energy is 14.5. And the mass is 150 grams. So you know the kinetic energy. So you can use EK equals half mv square. EK equals 14.5 into 10 to the power minus 3 to convert millijoules to joules equals half into mass is 150 grams. There is 0.15 kilograms. Into V square. From there you get the V subjective. What are you getting? 0.44 meters per second. Okay. Any questions, anyone? Question 3, page 4. Doctors can use ultrasound to monitor the heartbeat of a baby. Doctors can use ultrasound to monitor the heartbeat of a baby when it is developing inside the mother. A baby's heart was beating at 142 beats per minute. The frequency, 142 oscillations per minute. The wall of the baby's heart was moving with a maximum velocity of 22 meters per second, 22 millimeters per second. Calculate the maximum displacement in millimeters of the wall of the baby's heart. Assume that the motion of the wall of the baby's heart is simple harmonic. Can you give a try? Are you getting 1.48? Right. So guys, the frequency is the number of oscillations per second. So it's making 142 beats per minute, 142 oscillations per a minute, 60 seconds. So the frequency will be 142 over 60. Correct? And then to find the omega, omega equals 2 pi f, 2 pi into 142 over 60. I'm getting 14.87 radians per second. Correct? And then the Vmax, the maximum speed is given by A into omega. Okay, it's A omega, right? So A is the amplitude. So 22 is the Vmax given, which is in millimeters per second. So I will just leave it as it is because the A is required in millimeters. So A into the omega is 14.87. So you will get the A in millimeters 1.48. Okay. Right. The part B, the motion of the wall, maximum displacement is the amplitude. Amplitude is maximum displacement. So indirectly what they have asked is the amplitude. Okay. The motion of the wall of the baby's heart only approximates to simple harmonic. State what is meant by simple harmonic motion. So 2 marker, right? It's an oscillation where the acceleration is directly proportional to the displacement. It's an oscillation with acceleration directly proportional to displacement. And acceleration and displacement are in opposite directions. Acceleration and displacement are in opposite directions. Okay, right. Mark a few for homework.
So if you write the equation, will you get any marks? Because you write A is equal to minus omega squared x.
I'm not very sure. I can see, but I feel no. Question 9. Thirteen. 14. 'That's enough. That's it for the day. See you next week. Bye. Take care.